All right, so we're starting chapter 9, and chapter 9 we talk about the conic sections, and you'll understand what that means in just a second. But the first one we're going to talk about is the ellipse. Now, mathematics is present in the movement of planets, bridge and tunnel construction, navigation systems used to keep track of ships' locations, all kinds of things. The conic sections that we talk about, you're going to hear conic sections referred to as long as you talk about higher level math. And here's where they come from. They come from what's called a set of napped cones. It means that they intersect at the vertex there, and they're stacked where the center line is common through both of them. Now, if you take a plane, a flat surface, and you run it through this set of cones, you're going to come up, depending on how the orientation of that plane is originated, you're going to come up with different figures. For instance, if you go perpendicular to that axis of the cones, you're going to get a circle. If you go just off of perpendicular to that, you're going to get an elongated circle, which is an ellipse. If you go even further, you're going to get a parabola because one end of the circle is going to end up opening up. And then if you continue to go, rotate around, kind of rotating it clockwise here, that plane is going to actually intersect both of these cones, and you're going to have what's called a hyperbola. So that's where these conic sections that we're going to talk about come from. Now, one way that you can draw an ellipse is that you can put two tacks in a piece of paper, cardboard, or whatever you're trying to draw it on, and get a piece of string that's longer than the distance between these two tacks. You want it to be longer than that so that you can stretch it out. And if you push your pencil out like this and draw around, you're going to form an ellipse. That in itself comes from the definition of an ellipse. And the definition of an ellipse is this. It's the set of all the points, the sum of whose distances from two given points, which are called foci, F1 and F2 here, is a constant. So what that means is this. We've got our two foci of this ellipse. If we measure the distance from this point to that focus and this point to that focus, add those two distances together, we're going to get a number. And then if we move over to this point and we do the exact same thing, measure the distance from here to there and here to there and add them up, we're going to get the exact same number we did with this point. And that's going to be true for any point that you choose anywhere on the ellipse. So that's where this string comes in, because what do we know? Once we tie that string, is the string going to get, if it's inflexible, and you keep it taut, the distance that you're drawing here is just the length of the total length of the string, and that's going to be the sum of the distances from the two foci. So that's where the definition comes in. And here is the definition of an ellipse, actually, where you can copy it down. Figure 9.2 we looked at illustrates how to draw it. And you can read that if you want to. You can pause it and read it. I'm not going to read it to you. And the same thing with this down here. Now, more to focus to make sure that you get the two fixed points inside of the ellipse, are called the foci. And that's the plural focus. So it's the focuses. The midpoint of the segment connecting the two foci is the center of the ellipse. So if we were to go back and look at this picture right here, right in here, if we drew a line from focus 1 to focus 2 and found its midpoint, that is the center of the ellipse. And that's usually where you're going to base a construction off of. All right, now, here's the center again, and of course there's the center again. 9.4 that we're looking at right here illustrates that an ellipse can be elongated in any direction We're primarily going to look at the ones that are going to be horizontal, like this one, or vertical elongation, this way. There are situations where you have elongation along a diagonal. We're not going to look at those, don't worry. The line through the foci intersects the ellipse at 2 points called the vertices. So here's the major axis, it's the long one, and it's going to end when it intersects those points, the actual ellipse itself. These are called vertices, and we're going to call these major vertices. We're going to call these minor vertices. Just like this, the long axis is the major axis, and the short one is the minor axis. And once again, you can see with the major axis here is horizontal, major axis here is vertical. Now, the standard forms for the equations of an ellipse, and you're going to need to know these are not going to be given to you. The standard form of an equation of an ellipse with center at its origin and major and minor axes of length 2a and 2b, where a and b are positive and a squared is greater than b squared, is these two things right here. Now notice that there's a plus in between, so it doesn't matter what order these are in. The thing you got to focus on is right here. A squared is greater than b squared. Now what we're going to find is that when the a squared, the larger number, is under the x, then we have a horizontal major axis. When, like we've got it in the second one here, the larger number, the a squared is greater than b squared, that larger number is under the y, we're going to end up with a vertical major axis. That's a huge, huge, huge thing that you need, property that you need to know and remember. Now, the length of these minor and major axes are also based on the values of a and b. So on this one, we've got a squared. We're going to go out a in this direction, and we're going to go out a in this direction to get to our major vertices. Our b, which is our smaller number, we're going to go from the origin up and down, since this is a horizontal major axis. And you'll notice over here with this one, it's exactly the opposite. Because the a squared under the y, we're going to go up a and down a to get our major vertices, left b and right b, other way around, left b and right b, to get from your center to get your minor vertices. Now you'll also notice in here that there is a c value. Notice there's a c that used to get to the foci. Well, right here is how you find what c is. C squared equals a squared minus b squared. So kind of like the Pythagorean theorem, but subtraction. Now here's the way. We're going to use this exact same type equation again, but it's going to be plus. And we're going to use that for the hyperbola. So one of the things you need to remember is that if the equation for your function, actually it's not a function, never mind. The equation for your expression is a plus here, it's going to be the opposite here. And you'll see that when we get into the hyperbola stuff. This was minus and that's plus for the hyperbola. Also, here's another way that you can remember that it's minus. If we go out a here, we know that c has to be less than a to be inside the ellipse. So that's where we get the a squared minus the b squared. That's another reason that it has to be minus. So use your brain. If you end up accidentally doing plus, your c squared is going to be larger than a, and that means if you go out c this direction, you're going to end up with a focus out here somewhere, and that's not true. It's impossible, actually. All right, so let's graph an ellipse. In this case, it's centered at the origin. And if it's not centered at the origin, we're going to see this in just a second, but it's going to be something similar to the equation of a circle, where you would have like x plus h, sorry, that should be a minus, x minus h quantity squared and y minus k quantity squared. That's when we start having shifts of the center. We'll deal with that in just a second. So right now, let's look at this one. First things first, find the center, which of course we now know is at 0, 0. And then look for your A and your B. Well, A is going to equal the square root of this. So A squared equals 9. That gives me A is equal to 3. And B squared equals 4, which means B equals 2. Now, is this a vertical major axis or a horizontal major axis? Well, if you look at 9, it's the larger of the two denominators, and it's under the x, which means that we're going to have a horizontal major axis. So I'm going to go 3 out this direction, and there is a major vertices right there. I'm going to go 3 to the left from that center, and there's a major vertices right there. I'll go ahead and mark that center, vertex, vertex. And then I'm going to go 2 perpendicular to that major axis, and that's going to be from the center, and that's going to be my minor axis. 1, 2, and 1, 2. All right, so I've got enough right now that I could actually sketch this curve. Remember, this is it's actually a gradual. Don't try to connect the dots with lines. That's not how this thing works. It's a stretched circle, so you need to have a nice smooth curve all the way around. It doesn't have to be pretty. Look at my picture. It's awful. All right, and we're missing one thing. Yep, these vertices as well. We're missing one thing, and that are the foci. Well, and they ask us to find it. So we've got to locate the foci, and that's going to be C. Well, where do we get C from? Well, we know C squared equals A squared minus B squared. We know what A squared and B squared are, so we get 9 minus 4 equals 5. That's what C squared is. So C is the square root of 5. Now, the square root of 5, you don't have to grab a calculator and come up with a value for this. Just kind of imagine about what it is. The square root of 4 we know to be 2. The next square root that's a perfect square is 9, and that's 3. So we're way closer to 4 than we are to 9. So I'm going to imagine that that's probably about 2.2. So I'm just going to go from the center, 1, 2.2. Foci 1, and then 1, 2.2, foci 2. And when you list all these out, you're going to have to list all those points. So your major vertices, let's do that. Let's do this capital M. Capital MV are the major vertices, and we'll do little m V for the minor vertices. So the major vertices are going to be at 3, 0, and negative 3, 0. you could just do plus or minus 3, comma 0. Your minor vertices are going to be up 2 and down 2, so that's going to be 0, 2, and 0, negative 2, or just 0 plus or minus 2. And then your foci are going to be square root of 5 and negative square root of 5. So plus or minus the square root of 5, comma 0. And like I said, you are going to have to list this stuff out when you graph it. You just can't draw a graph and tell me where that comes from, and say that that's it. You got to show me all the work to tell me where all that stuff comes from.
All right, so continuing on, we
are not always going to see our equations set up perfectly in the ellipse equation we've just been talking about. Sometimes you're actually going to have to rearrange it algebraically to get it in that form. So in this case, we're going to graph and locate the foci of this ellipse. Now this is an ellipse as well, and I'm going to show you exactly how I know that. First of all, we know that because we don't have x squared and y squared with the exact same coefficient. That means that it's going to go further in one direction than it does in the other. And the 400 over here, that's just something we're going to end up moving to this side. Remember, when we go back and look, we have 1 over here when we've got this thing in standard form. So that's one of the things we want to do, is we want to get 1 over here. So we're going to divide by 400 on both sides. Now if you divide by 400 over here, it's cool, you get 1. Over here, remember, you have to divide 400 into both parts. So you've got 25 x squared over 400 plus 16 y squared over 400. And all you want to do now is just simplify that. Well, 25 will go into 400 8 times. No, 16 times. So you got x squared over 16, and then 16 goes into 425 times. So you get y squared over 25, and then that's going to equal 1 on the other side. All right, so now we have this in standard form. So we know that a is going to be our largest denominator, which is going to be this. Well, a squared is going to be that. 25, so a equals 5. B squared equals the other one, 16, which means that b equals 4. And to find what my c is, c squared equals a squared minus b squared. So when I plug that in, I'm going to have 25 minus 16, which is going to give me 9 for c squared. That means that c is going to equal 3. Now, looking at this equation right here, what do we know about the way the orientation of our major axis? Remember, the orientation of the major axis is determined by what's the largest number on the bottom and what it's under. So we've got 25 under y squared, which means we're going to have a major axis that's going to be vertical. We have our center at the origin. Major axis has lengths of 5 in both directions, so I'm going to go up 5 and down 5. And then with my minor axis, I'm going to go left and right 4. All right, so at that point, I can sketch my ellipse. Like I said, they don't have to be pretty, but don't make an ellipse because of our 4 points into some kind of diamond or rhombus. It needs to be curvy. Even though it's not pretty, it's still curvy. All right, and then what do we know about C? Well, C is going along our major axis, which in this case is vertical. So we're going to go up 3 and down 3, and that's where the foci are. All right, so when we list everything out, we need to list all our points. So let's look at the major vertices. They are at 0, 5 and 0, negative 5, so 0 plus or minus 5. And minor vertices are going to equal 4, 0, and negative 4, 0. So plus or minus 4, comma 0. And then your foci are going to be up 3 and down 3, so you're going to have 0 plus or minus 3. All right, other times you're going to be given information about the ellipse and asked to find the equation of that ellipse. So it says find the standard form of the equation of an ellipse with foci at negative 1, 0 and 1, 0, and vertices, this is major vertices, at negative 2, 0 and 2, 0. When they talk about vertices, they're talking about the major vertices. All right, so what do we know? Well, what is going to be the midpoint from the point negative 1, 0 to 1, 0? Well, that's going to be 0, 0. Well, guess what that is? That's going to be the center. So if the center is at 0, 0, and I go from negative 1 to 0 to 0, 0 in one direction for the foci, and from 0, 0 to 1, 0 on the other direction for the foci, what do I know about my ellipse? Well, I know that if I'm going to my foci, that is the value of C. So I went negative 1 and positive 1 for C. That means it's, or to the foci, so that means C equals 1. If I go to the vertices, negative 2 and 2, that means that A equals 2. And if you need to go back and look at that picture where we drew that, go back and look at it, because you need to understand this, because we're going to talk later about situations where the ellipse is not going to be centered at the origin. It's going to be really confusing then. So go back and make sure you understand why I have these values right here for C and A, from getting C from this and getting A from that. Now, if I know what A and C are, guess what I can find? I can find what B is, because I know A squared minus B squared equals C squared for an ellipse. Well, if I know 2 out of the 3 variables there, I can solve for that last one. So when I plug everything in, I'm going to have 1 equals 4 minus B squared. And then, of course, we're going to move that 4 over to the other side. We're going to get negative 3 is equal to negative B squared. And that means that B, when I cancel out or divide both sides by negative 1 to get rid of the negative, that means B is going to equal the square root of 3. So now when I write the equation centered at the origin, which way is my major axis going to be? Well, if I'm moving from negative 2 to 0 and from 0, 0 to 2, 0, what's changing, my x or my y? Well, your x values are changing. That means you're going to have a horizontal major axis. That means your largest value, A, is going to go under your x. So we have x squared divided by a squared, which is 4, plus y squared over b squared. Well, if b is the square root of 3, what happens when I square that? I'm going to get 3, and equals 1. Now, guys, remember, this is not what I found for c. That is always, always, always going to be 1. c is not in this equation anywhere. c is found by this other equation. Now, as I talked about just a second ago, ellipses are not always going to be centered at the origin. Horizontal and vertical translations can be used to graph ellipses that are not centered at the origin. X minus h, quantity squared over a squared, plus y minus k, quantity squared over b squared, equals 1, and x squared over a squared plus y squared over b squared equals 1 are these two equations. The blue one is this one. The purple one is this equation over here. So we actually shift over h and up k. Now, the reason we're going over to the right and up is the fact that both of these numbers are positive. Guys, understand it's kind of like the equation, it's not kind of like, it's exactly like the equation of a circle, where whatever you got in here, you want to change the value. You want to change the sign of it. So if this is x minus 2, treat it as a plus 2. If this is x plus 7, change the sign and treat it as a minus 7. So for both of those, you need to change the sign when you go to do your shifts. All right, this is information that you need to know how it's going to affect everything. If the center is HK, then from that center, that's where you're moving for your major axes, your major vertices and your foci and your minor vertices. So you're not going from 0 to 0 anymore, so it's not quite as easy as it was. Now you've got to go from HK, wherever that center might be. Everything else is exactly the same, though. You're still using A to determine which one your major axis is. You're still using A to determine how far you go along that major axis to get to the major vertices. You're still using B to find how far out from the minor vertices, or how far out the minor vertices are from the center, perpendicular to that major axis. And you're still solving for C exactly the same way, and finding and using it to find out how far along that major axis you go to find where the foci are. Nothing else changes. You're just shifting the center, which is where you're starting, to a different place with these translations. After that, you're just counting in both directions. All right, so let's do one of these. We're going to graph x minus 1 squared over 4 plus y plus 2 quantity squared over 9 equals 1. And they also want to know where the foci are located. All right, so first things first, let's identify the center. The center is going to be at 1, -2. So 1, -2, right there. Now, what direction is my major axis? Well, it's vertical. And the reason why is my larger number is under the y. The larger number being under the y means the major axis is going to go in the y direction. All right, and now let's find out what A is, what B is, and then we'll find out what C is. So we know that A is going to be the square root of 9, which is going to be 3, because this is A squared. B is going to be the square root of 4, which is 2. And then C, well, we know that C squared equals A squared minus B squared. So that means we've got 9 minus 4, which is 5. And that's C squared. So C is the square root of 5. We already talked about that. We're going to think about that as approximately 2.2 or so. So if our major axis is vertical, we're going to use A to go up 3, 1, 2, 3, to find one major vertex, and then from the center again, I'm going to go 1, 2, 3 to find the other one. I use B to go perpendicular to that major axis there, to the left and the right in this case, to find out how far out my minor vertices are going to go. So 1, 2, and 1, 2. Now at that point, you can go ahead and sketch your ellipse. Get an idea of what it's going to look like. Remember, it doesn't have to be pretty, but do not draw straight lines. And then what do we know about C? Well, C is going to tell us where the foci are, and the foci are going to be along the major axis, square root of 5 out. Well, like I said, square root of 5 is roughly about 2.2, so we're going to go 1, 2.2, and then 1, 2.2. Now we need to write down all these points, so we're going to have to go back and do some thinking. But remember, everything's going to come from that. Now the reason I went ahead and did the graphing is because it's going to be a lot easier to recognize this stuff now and check it as we're doing it. So we know the center, we've already listed it, we don't have to list it again. And the major vertices are going to be where? Major vertices are going up from there, so my x value is going to stay the same. So I've got the points 1, comma, and then if I go from this point up 3 units, I'm going to have positive 1. And if I go down 3 units, I'm going to have negative 5. So I have 1, negative 5. So all I did was take this center and I did what? I added 3 and I subtracted 3. So it's the same things we've been doing. With a plus or minus, only in this case we're actually having to add it to something other than 0. All right, and then let's find our minor vertices. So once again, we're starting at our point and we're moving left and right. So what's going to change if we move left and right? Just the x values. So I can go ahead and write down my y values of negative 2 for both of these. And then what do I know? From 1, I add 2 and get 3. And from that 1, I'm going to subtract 2 and get negative 1. So there are my minor vertices. And then your foci, same thing as the major vertices. You're changing your y value only. So you got 1 and 1. Now with this one, especially if it's not a whole number, if it's an irrational, a square root, something like that, I'll give you the ability to just go in and say, just write it one time. I don't want you to do that with these other ones. But in this case, I will let you go in and say negative 2 plus or minus the square root of 5. And this is giving you negative 2 plus the square root of 5 and negative 2 minus the square root of 5. And that's these points right here. All right, that's it.